I'm very I'm very happy to introduce the first speaker today. So it's Professor Héctor Pastén from Pontificia University Católica de Chile. Okay, so you can see the title of his talk from the slide, so I don't need to repeat. So let's welcome Professor Pastén. Okay.
Okay, thank you very much for the introduction, and also thanks for the invitation. I'm really happy to speak here at this seminar. Well, about the name of the university, it's hard to read even in Spanish, so no worries about that. Okay, so let's see. The topic for this talk is Hilbert's problem for rings of integers of certain number fields of degree 6. So I'm going to try to explain what this is all about and what does it have to do with the topic of the conference, okay? So let's start with the basics. So what is the Hilbert's problem and what are the Diophantine sets? All right, so the basic question that motivates this whole business is the following one by Hilbert, posed by David Hilbert in 1900. And the question is this: to devise an algorithm that takes the Diophantine equations over Z, the integers, as an input, and then the output of this algorithm should be yes or no. Do you have solutions in the integers or not? Okay, I'm not asking for an algorithm to solve the equation, just to decide whether or not you have solutions, which is a priori a weaker question, okay? And the theorem, and this is not a heuristic, this is actually a mathematical theorem, is that this is not possible. So Hilbert was asking for an algorithm to do this. The answer is that there is no such thing. There's no algorithm like this. Of course, if you want to prove a theorem like this, you need to formalize what algorithm means, okay? But today is agreed that algorithm has a mathematical meaning, and this mathematical meaning is a Turing machine, or recursive functions, or, well, many of the other equivalent definitions, okay? So there is a well-defined mathematical context in which this question makes sense, and the answer is that there is no algorithm of this sort, okay? But, well, first, in the number theory session webpage, you read this. It's about the interaction between arithmetic geometry and automorphic representations, okay? And it also says that the idea is to explain the latest discoveries in this topic. So, natural question: what is the relation? What does the unsolvability of H10 over C have to do with? What is the relation with arithmetic geometry and automorphic forms or representations? Okay. And the answer is that there is no relation, okay? It doesn't relate, all right? But that's fine, yet, okay? So in a moment, you'll see that there is, in fact, a relation, okay? So Diophantine sets, well, this is quite important for the topic today. A Diophantine set, you can define this notion in general for commutative unitary rings, and that's what I'm going to do here. To take a ring A, and a set in such some Cartesian power of A is going to be called Diophantine if there is some affine variety X defined over the ring with some morphism to affine space with the property that when you map the A points, you get exactly S, all right? So you have your affine variety, you have a morphism to some affine space, you look at the A points in this affine variety, and only the image of that is what you consider. That's going to be called a Diophantine set. And the reason you call it this way is because if you go back to the basic case of the integers, for A equal to Z, this is exactly the same thing as requiring that there is some polynomial in two sets of variables, the variables T and the variables X, with the property that the set S that you want to consider is obtained as taking the integer solution set of the polynomial and then mapping onto the first couple of coordinates, okay, the T coordinates. So you forget a couple of other coordinates. All right, so it doesn't look quite the same. I mean, if you, well, one direction is obvious. If you have the polynomial, then the zero set is the affine variety. It will be really ugly, but it doesn't matter, okay? It's the affine variety, and then the projection map is the morphism. But in fact, you can go the other way around, and the reason is that over the integers, the zero set doesn't really care about the geometry of the variety as long as you have the same zero set, okay, the same solutions. And you can take intersections of hypersurfaces and unions of Zariski closed sets just by looking at the sum of squares that will give you the intersection or the multiplication of the equations that will give you the union of the solution sets. Of course, not over the complex numbers, but over the integers, that's perfectly fine. So you can reduce everything to just one polynomial equation. Good. So here's an example. So if you remember your first year undergrad, inequality is not a symbol, it's actually a subset of the second Cartesian power. It's a relation, a binary relation. So this subset of the second Cartesian power of the integers is the binary relation given by x less than or equal to y. So it's a set of pairs, right? And this set of pairs, although it's not the zero set of a polynomial, it is Diophantine. And the reason is that there is this basic theorem of arithmetic, really beautiful, but old stuff, that you can write every non-negative integer as a sum of 4 squares of the integers, right? So you have this polynomial equation in 6 variables, and every solution that you find, when you project onto the xy coordinates, you get a pair in the relation. X is less than or equal to y. So you have a 6 variable polynomial equation. You look at the integer solution set, you project onto the xy coordinates, that's 2 coordinates, and then you get your set. So that means that less than or equal to, that's a Diophantine relation, a Diophantine set. But this is just an example. It's not that I'm going to use this particular one. All right, now a different kind of sets are the listable sets. And a listable set is a set that can be listed, basically. Okay, so there is some Turing machine that you run your Turing machine, it starts working, right? And the machine will output sequentially the elements of the set X and nothing else, okay? Nothing else. It could be with repetitions, it could be in some random order, that's fine, okay? But every element of the set X is going to show up eventually in this list and nothing else. Okay, that's a listable set. And if you don't like Turing machines, you can think about recursive functions, okay? That is the same. There are many equivalent notions, but for the purposes of giving a talk, it's much better to think about an algorithm or a Turing machine or some Python program, okay? That's the same thing, okay? Now, every Diophantine set is listable. And the proof is really simple. The proof is this. You consider some polynomial equation that realizes this set as a Diophantine set. And then the polynomial equation or the affine variety, you look at the integer points, okay? So you can list these guys. How? You take the ambient affine space. You can certainly list the integer points in the ambient affine space. These points, sequentially you produce them, you plug them into the equations of your variety. If you get 0, it's good, you project and you find one element of your Diophantine set. If you don't get 0 when you plug it into the equations, then forget about this point, keep going, okay? So in this way, you start listing the elements of your Diophantine set, and no point outside the set will appear, okay? Of course, you can get repetitions. If the fiber has many integer points, you will certainly get repetitions, but that's fine. And this is algorithmic. That's the whole point. This is algorithmic. So there is some Turing machine doing this. And of course, some people actually wrote this down, but I'm not going into that. Right, and Turing himself proved that these listable sets are not just whatever you want, okay? They have some restrictions. Of course, you have only countably many Turing machines, so you can only have countably many listable sets, but there are more restrictions. So for instance, there are some crazy sets that are listable, but not the complement. So there is a Turing machine that can produce the elements of the set, but there is no Turing machine producing the elements of the complement. So there are crazy examples like this. And one example constructed by Turing is the really famous Harting set associated to the Harting problem, okay? Which is really beautiful stuff, okay? But for the purpose of this talk, just keep in mind, there is some set that's listable, the complement is not. Now, what's important about this is that in particular, it's not possible to decide membership to this set. You cannot decide membership because if you have an algorithm that decides membership to the set, you can use this algorithm to list the set and to list the complement. You just go through all the integers, apply your membership algorithm, and then according to the answer, you can write in list A or list B, okay? So this example shows that there are some sets that are undecidable for the membership problem. All right, so why all of this? Well, because in fact, Davis, Putnam, Robinson, and Matijasevich, they proved a much stronger theorem. It's not just undecidable. It's not that there is no algorithm like the one Hilbert wanted. There is something else going on. There is something more structural going on. And every listable set is Diophantine. So you actually have the converse. So give me any crazy listable set. I don't know. I mean, factorials of primes. So say, okay, factorials of primes. Well, this guy is listable. There is an algorithm producing the factorials of primes. And therefore, it's Diophantine. It appears as the projection of the solution set of some Diophantine equation. Okay, that's the theorem. And the proof is at the same time elementary and complicated, okay, but really beautiful. And basically what you want to do is to use Diophantine equations to mimic, to somehow behave as if they were Turing machines. So you mimic every part, every piece of a Turing machine using Diophantine equations, bit by bit, okay, little bit by little bit. But so at the end, you deduce from this that H10 is unsolvable using the halting set, because the halting set is listable, it's undecidable, but it is listable. And therefore it appears as projection of solutions of some Diophantine equation. All right, take that polynomial, take it. For each integer, you can evaluate on the first coordinate this polynomial, and you get some polynomial f sub a. And you can do this algorithmically. It's just evaluation of a polynomial. That's an algorithm that you can run for that, right? Well, if the algorithm requested by Hilbert actually existed, then for each integer, I could use this algorithm to decide whether or not this FA has an integer solution. But FA having an integer solution is exactly the same thing as A belonging to the set H, because P was cooked up in this way. Okay. Therefore, the algorithm that Hilbert wanted will be useful here to decide membership to H, but that's not possible, contradiction. Okay, so that's the thing, okay? So there is this way stronger theorem that structurally is telling you something about Diophantine equations, and undecidability is just a corollary of it. Okay, that's with it. Now, rings of integers. Well, we do number theory. We, of course, know that Z is not the end of the story. So you have a ring of integers for number fields, and arithmetic there is as interesting or even more sometimes than arithmetic over Z. And sometimes it's really necessary if you want to prove something, even it's classical, okay? So, of course, for the purposes of these undecidability questions for the Diophantine equations, it makes a lot of sense to ask the same thing about the ring of integers of number fields. Okay, so, well, that's a question, and this is the conjecture. The conjecture is that Z is a Diophantine set inside of any ring of integers. Give me any ring of integers, and Z is Diophantine there. Okay, and that would imply many things. So first, there is some not very obvious implication that you can transfer the DPRM property, listable equals Diophantine, you can transfer that from bottom to top if Z is Diophantine there. Okay, this requires a proof, which I'm not giving here today, but it's well known. So if you can somehow show that Z is Diophantine in OK, then in fact, every listable set in OK is going to be Diophantine. And you also will get the negative solution to Hilbert's problem for deciding solvability of Diophantine equations over rings of integers. So it looks like a very interesting conjecture from that point of view. And in fact, this H10 for OK remains open because we have no idea what to do with this conjecture. Okay. There is no logical implication in that sense. It's just that we don't know what else to do. If you want to prove undecidability here, the only thing that comes to mind is actually proving this. Z is Diophantine in OK. We don't really have many other strategies here. Okay, so the conjecture is known in some cases, not completely open. So some cases that will probably look very familiar to you if you work in the Langlands program are, but this is a coincidence. It's not really, there is something deeper going on here. It's just a coincidence. Well, there are some degree 4 number fields, but here's interesting, a quadratic extension of total real. That we can deal with, okay? Now, when K has exactly one complex place, we can also deal with that case. If most of the embeddings are reals, except for one, okay? Of course, these guys, most of the time, is not gonna be Galois over Q, but well, it's a number field, okay? And this particular item is important for us today, and it has proof by Thanasis Fidas, Alexandre Schlapentok, and Carlos Videla. This was before internet was a thing, so people, you know, prove. Those days, people actually proved theorems around the same time, maybe even months after. They had no idea that somebody else did it, but at least it's in print. In the three cases, it's in print, and it's very interesting that this development occurred more or less at the same time. All right, and there is something else, fields that can be included in a field of the previous kind, okay? How's that? Well, here's an example. And this is a theorem of Shapiro and Schlapentok, okay? So they prove, for instance, as a corollary, every finite abelian extension of Q. Why is that? Well, we learned in high school, right, the Kronecker-Weber theorem that says that if you have an abelian extension of Q, then it has to be contained in some cyclotomic extension. But cyclotomic number fields are quadratic extension of totally real. All right, so we know this, this theorem for cyclotomic number fields, and abelian number fields are contained in those, so you can transfer downstairs. Okay? You cannot transfer upstairs because otherwise, you know, from Q you get everything, but it doesn't work that easy. But you can transfer downstairs this, Diophantine property of Z being Diophantine in OK. All right, so that's a proof. So it's really useful, this final item, but of course this doesn't cover everything, okay? And the question is how to prove that C is Diophantine in OK in more generality. And the basic idea, the basic intuition, and actually this is what's behind the previous theorems that I mentioned, is that one tries to find some Diophantine equation over Z that has infinitely many integer solutions, and with this weird property that when you go to the extension, you don't get new solutions. Then in this way, you can use Diophantine equations to define plenty of integers in OK. And then you do something to get all of the integers. Okay, but this strategy works in many cases. In the first and second case, it works, okay? But that's it, and you need to do something else. But you can elaborate on this idea. And well, after a sequence of improvements and generalizations and modifications and many things, there is this theorem. This is the final version proved by Schlapentok in 2008. It says that if you give me a number field extension, and if you give me an elliptic curve over the bottom field, with this property that the rank is positive over the bottom field and remains the same over the extension, then you're good, and the ring of integers over the bottom field is Diophantine over the top field. Okay. So the elliptic curve will play the role of this equation, is not over the integers, but technical stuff happens on the way, and this is the criterion. If you can produce elliptic curves of this sort, mass production of elliptic curves of this sort, then you can deal with the conjecture. You can define the ring of integers downstairs, upstairs, and of course you would like to apply this for Z contained in OK. So just to make sure we all understand what's going on here. Here's an example. You take Q adjoint the fifth root of 2. This looks like a random example, but it's important because it's an example that's not contained in the list I mentioned before. Okay, the results I mentioned before do not apply in this case. So this is a very simple case that it was open before the elliptic curve stuff. But well, here's the explanation why it's not covered. But the important thing is that you have this elliptic curve. This is the Cremona label, 58A1, the conductor is 58. And the important thing about this elliptic curve is that the rank over Q is 1, and the rank over this extension is 1 again. So if you get anything new, it's just going to be torsion. So for all practical purposes, this Diophantine equation is picking up plenty of rational numbers that you still get them and nothing else when you go to the extension. So you can start playing with that and finally define C that in a Diophantine way inside of OK. So this proves that C is Diophantine in OK, thanks to the elliptic curve criterion. All right. Good. Okay, that's good for one example. Okay, so it means that the elliptic curve criterion is useful, but how about the general case? Okay, can we somehow produce these elliptic curves in all cases? Well, we'll see. There is this corollary that in fact, you don't need to deal with every possible extension of number fields. it's enough to deal with quadratic extensions of number fields, but then it has to be relative quadratic, okay? So not just quadratic over Q, but relative quadratic. Give me any number field, and you have to be able to produce the elliptic curves for all quadratic extensions of this one, okay? But that's fine. I mean, quadratic extensions are not too bad, and you just want elliptic curves over number field F that retain the same rank, positive rank over number field L, quadratic, okay? So, okay, how's this? This looks like black magic when you see this. How's that you can reduce the whole story just to quadratic extensions? But and you see that this version of the reduction is from 2018. It's quite recent, okay? So here's the proof by Schlapente, really smart argument, okay? Take your number field, the number field you want to deal with. You can transfer downstairs. So you can enlarge K and deal with that one. So you may assume that K over Q is Galois. All right, so for every subfield F, so that the extension F to K is quadratic, by assumption, we have OF Diophantine in OK, by assumption, assuming that we have the elliptic curves, right? And all right, so intersect these OFs, okay? Intersection of Diophantine sets is again Diophantine. You just play a bit with the equations, with the Diophantine equation. So this intersection is going to be Diophantine inside of OK. But then what is this intersection? It's the ring of integers of a totally real number field, because when you take quadratic extensions, you are picking up also the fixed field of a complex conjugation. So when you're running over complex conjugations, you pick up these fixed fields, and then when you intersect, in particular, you get this totally real thing. You kill every complex embedding. All right. But then we know what to do with totally real since the 80s. Okay, so that's it. You can do this transfer by steps. Okay, so if this is Diophantine in that and this is Diophantine upstairs, then you can go from, if you can go from bottom to middle and middle to top, then you can go from bottom to top. That's part of these functorial properties of Diophantine sets. Okay, so that's it. Great, looking good. So can we settle the conjecture then? No, okay, but at least we know something. The elliptic curves that we need now for quadratic extensions, they should exist. They should exist. If you are willing to believe standard conjectures about elliptic curves. So on the one hand, there is this squareness conjecture for the two torsion of Shah. Okay, now one has to be careful here. So if you give me just some abelian variety and you look at the two torsion of Shah of this abelian variety over a number field, there is no reason for this to be a square. Okay, even for GL2 type abelian varieties over Q, you know, there are examples where you don't get a square. And the reason is that the Castle state pairing is about abelian variety A with a dual. So it's not actually a self-duality. But over elliptic curves is fine. So you actually do expect squareness for elliptic curves. Okay. So that's a very reasonable conjecture, and Maser and Rubin, they show that this is enough. This will imply the existence of the elliptic curves you want, and then that will settle the problem. Now, that's kind of an algebraic approach, and we have an analytic approach using L functions with Ram-Murthy. So we prove that if elliptic curves over number fields are automorphic, well, you don't need all of them, you just need conveniently chosen ones, okay? But if they are automorphic, and they satisfy the rank BSD, which again is not the full rank BSD. It's just an analytic rank 0 implies algebraic rank 0 plus parity. It's two parts, okay? If you have that, then the elliptic curves you want, they also exist. Good. Good. So let me just give a brief idea of the proof of item 2. How do you get the elliptic curves with positive rank, preserving the rank in quadratic extensions from you know, this property of being automorphic. So okay, fine. Let's say that the elliptic curve is automorphic, so the L function comes from some automorphic representation, suitable type, right, for GL2 of the ideals over K. So there is this theorem by Friedrich and Hofstein from analytic number theory that says that then you have infinitely many quadratic Hecke characters that when you twist and you evaluate at the center point, you get non-zero, okay? So if you are in the BSD business, this kind of theorem should be familiar to you, because it's the kind of tools you need to transfer the Gros-Saguier kind of theorems into BSD kind of theorems, okay? Using, of course, Euler systems of all of that. So you need this sort of non-vanishing. So this is a very standard tool in that setting, but we have it here also, right? And there is a little lemma that if you give me a quadratic extension of number fields, there are infinitely many elliptic curves over the bottom field that acquire negative root number over the top field. And this is not entirely obvious. You really need quadratic here. So there is this example due to Docklister, I think, that they show that there is this biquadratic extension of Q with the weird property that give me any elliptic curve over Q, and the root number over the top field is 1. Okay, it's not very well known, but this phenomenon happens. So there is something to be shown here. It's not for free. All right, fine. So, well, you may assume that the elliptic curve E has root number 1, and the quadratic twist by L has root number -1. Okay, this thing splits for the quadratic extension. Upper L means quadratic twist by L. Now you take a quadratic character with a non-vanishing property for the twisted elliptic curve, and with the congruence condition that the root number that appears here is -1. So of course, this is not for free. You need to check that this condition is not obstructed. Okay, but it's not obstructed precisely because of the previous lemma. The elliptic curve of the previous lemma shows that, this condition, you know, there is at least one example, therefore it's not obstructed. All right, so what's the deal here? Well, non-vanishing of the L function is analytic rank 0, and therefore implies that the elliptic curve here, the twisted elliptic curve, now is twisted by L and by eta. The twisted elliptic curve has rank 0. And then the root number -1 implies that the rank is odd under parity, okay? And odd numbers are usually positive. So, well, if bigger than or equal to 0 means strictly bigger than 0 for an odd number, which is a silly thing, but it's really important. So you get that. And that's it, okay? So if you want to control the rank in a quadratic extension, the rank splits between the rank of the elliptic curve and the twisted one. So one has to be 0, and that is enough to say that the other one is preserved. Okay, good. Good, so that's very promising. So we have two conditional results, completely independent one from the other, implying that we should expect this elliptic curve. So we should expect a positive answer to the problem. We should expect undecidability in full generality. But how about proving something unconditional? Here, well, you see, until not so long ago, the only results unconditional for infinitely many cases, of course, because cases one by one you can check with the elliptic curve criterion. But for infinitely many cases, is the least we had since the 80s. Okay, so the story went up to 89, and that's it. Okay, after that point, it's only particular examples one by one. So there is this proposition. It's just a little silly trick that we figured out with Natalia, my co-author. We figured this out in 2017. Okay, it took some time to actually use it for something good, but the criterion is this. So you take L and F, two number field extensions of a bottom number field M, and L has to be quadratic over M. Okay. Now, suppose that there is some elliptic curve over the bottom field that behaves in a different way in both directions, okay? In the quadratic direction, you get positive rank. In the other direction, you get rank 0. So, of course, over the bottom field already had rank 0. Then, OF is Diophantine in OK. Now, of course, too many letters, so I have a diagram in the next slide, okay? So don't worry if the thing looks too confusing, there's some picture, okay? But the important thing is that there is some criteria to produce extensions that are Diophantine, okay? But you may say, well, what's the point? I mean, we already had a criterion using elliptic curves. Well, you'll see. There is the proof, maybe, yeah, it's short, I can just say it, okay? So if you have the elliptic curve, you take the twisted one by L. All right. So L is contained, so the twist by L doesn't do anything over K, and K contains L, so the rank can only decrease. But over L is supposed to be strictly positive, so you have this chain of relations, right? But then item 1 implies by this little trick of splitting by twist that the rank is preserved. You put these two things together, and then you get an elliptic curve over F with positive rank that retains the same rank over K. And that will be the elliptic curve EL. All right, so this is the picture. So you have this diagram of fields. You want an elliptic curve over the bottom one that in the quadratic direction has a positive rank, in the other direction has rank 0. Okay, if you give me an elliptic curve like this, then this F is has OF Diophantine in OK. Okay, so it's some auxiliary construction here. Okay, just to keep in mind where the thing is. All right, so here's the result. Okay, it says 2017. It says 17. It should be, I think, 19. That's a typo. Yeah, it took 2 years to actually use that little construction for something good. Okay. Wait a second, it's compiling. Okay, good. Now we have a 9. All right. So there are explicit Chebotarev sets P and Q of positive density in the primes. Okay, in the primes, so that for every P, little p in the first one and little q in the second one, chosen independently. Okay, it's not that one depends on the other. You can choose them as you want. You have that C is Diophantine in the ring of integers of this weird field. So what is this weird field? Degree 6 extension of Q. You put some cubic root and some quadratic root of primes, okay? But it's really explicit, okay? So our construction gives the set P has density at least 31%, and the set Q has density at least 8%. And the set, when I say explicit, I really mean explicit. So you can just sit down and write elements. So here are the first few elements of the two ones. I stopped at 79 just to show that it's possible for a prime to appear in both. Okay, it can happen. But you can keep going, and it's not too bad to actually write down elements of the sets. So why these fields? Well, these fields have an interesting property, is that they are not contained in the list of known cases for the DPRM conjecture for OK. So for these fields, we do not know if Hilbert's problem is unsolvable for the ring of integers. Okay, so they are truly new instances of the conjecture. And in fact, this is the first thing going on, for some explicit concrete family. Here it is, infinite concrete family, since the 80s. So it's been some time. Good. All right, so the fields show up in this way. You have the quadratic direction with square root of minus q, and the cubic direction, okay, which is some other thing. And then the construction, the elliptic curve criterion with the little trick I mentioned before. If you find the elliptic curve over q doing this and that, then for this extension here, you get the Diophantine property that OF is Diophantine in OK. All right. Now, why is that enough? Because Q of cubic root of P has only one complex place. Okay, two complex conjugate embeddings, only one complex place. So we know the conjecture in this case. So if you have Z Diophantine in OF, which we have, and then thanks to this construction, you have OF Diophantine in OK, and then you have Z Diophantine in OK. So we actually chose this kind of fields precisely because for this cubic root kind of fields, you have the conjecture already proved. So you can use this, as a point, intermediate point in the construction. Okay, so that's what I mentioned. So we need to achieve rank 0 in the cubic direction and rank positive in the quadratic direction. That's the goal now for some elliptic curve here. And of course, we need to do this, mass production of samples because we want positive density of P's and positive density of Q's. All right, so the rank 0 thing, we actually do it by Iwasawa theory. So here's, well, you already saw some automorphic stuff going on, but now there is some arithmetic geometry going on, okay? So the thing is that it's hard to control the rank of elliptic curves. And it's even harder if you want to go to extensions, okay? So there is no recipe for that. But Iwasawa theory is actually well designed for extensions. I mean, that's the whole point of the theory, right? How things behave when you go to extensions, to towers. So the Iwasawa invariants, actually, you can have a bit more of control for them. And that's good because the rank of an elliptic curve is bounded by the Iwasawa lambda invariant. Of course, there are some assumptions in the middle, but let me not go into details there. So here's the basic setup. You take some ZL extension. So my prime is going to be L because P is already taken, okay? Some ZL extension. And then you assume that your elliptic curve is ordinary at L, and you have a Selmer group here, the infinity Selmer group here, okay? And the dual thing is going to be the model where you want to develop your Iwasawa theory. This is the setup in Mazur's paper of points in towers, okay? Points of abelian varieties in towers, where, Iwasawa theory for elliptic curves and abelian variety is not due to Iwasawa. It's actually, developed initially by Barry Mazur. So, all right, so this is the model where you do it, not a class group. It's actually this dual of Selmer. Okay, and it's going to be a finally generated lambda model over this power series ring. And it's conjectured to be torsion. In the case we care about, one can actually prove it is torsion. So there's this classification theorem that will tell you that you can up to pseudo isomorphism, so finite kernel, finite cokernel, is going to be something like this. Okay, direct sum of killing powers of primes and killing some polynomials. And the polynomial part, when you look at the degree, that tells you what the lambda invariant is. It's a measure of the size of this set X, in the sense that you look at the degrees of these polynomials that show up in the classification. All right. So yeah, and you see that there is a Selmer group at the back here. Everything is running on this Selmer group. So there is no surprise that you can track down what is the relation between lambda and the rank of the elliptic curve. There is, of course, a lot of material going on there, in particular Mazur's control theorem. But, Selmer groups are here, so no surprise that you should expect to see a rank somewhere, okay? All right, so the lambda invariant, you can actually understand how it changes when you go to an extension of the bottom field, provided that extension is an L power extension, okay? L extension, say. So you can see what's going on there and write it down, pack it really nicely, and then you get a theorem. So here's the theorem. You take an L bigger than 2, and you take an elliptic curve that it's ordinary at L, because I want to do some Iwasawa theory, and residual Galois representation is surjective, and the rank over this cyclotonic extension is 0, and the L torsion of Sha over the cyclotonic extension is 0 also. And L does not divide the Tamagawa number and this number of points of the reduction. Okay, so of course the theorem is not just going to be conditions. There is some conclusion here. The conclusion is that there is going to be a Chebotarev set of primes of positive density with the property that the lambda invariant is going to be 0 over this extension. So you cannot join the Lth root of P. It's going to be there. Okay. So there are plenty of conditions, but if you look at them again, well, if you fix L, this is something you can check. You give me an elliptic curve and I can probably check this using some descent argument. Okay. It's just, the L torsion of Sha is not the L primary part of Sha. L primary part of Sha, is a nightmare, but the L torsion is just coming from descent. And we're going to use this for L equal to 3. Okay, why 3? Why 3? Well, for 3, you get the lambda invariant over this extension is going to be 0, and in a very particular, consequence, a very particular consequence is that the rank for the cubic root of P extension is going to be 0. because it's bounded by this lambda invariant. In fact, you can throw in here the cubic roots of 1, but I don't need to. And the reason I stick with this L equal to 3 is because in in general, you have a result here for any odd prime L, but I want to apply this to a logic problem. And of all these cases, Lth root of primes, where the rest of the theory is going to apply, only L equal to 3 has exactly one complex place. So we are lucky, there is some non-trivial intersection between the logic stuff and the Iwasawa theory thing. So there is something there, okay? So that's why we take L equal to 3. In fact, the theorem is much easier to prove for L bigger than or equal to 5, but then you cannot use it. So you need to, suffer a little bit to make it work for L equal to 3. Okay, good. How about the positive rank? Well, positive rank is going to come from the modular side, not the Iwasawa side. It's going to come from Heegner points. So when you take an elliptic curve over Q, by the wonderful modularity theorem of Wiles and others, we know that it's going to be modular, so it's going to show up as a quotient of a modular Jacobian, okay, over Q. Now, in the modular Jacobian, you can produce these points called Heegner points. How? Well, you take a quadratic imaginary field satisfying some congruence condition, the Heegner condition, and that produces a point in the modular curve. And this point is going to be in some Hilbert class field, okay? You map it to the Jacobian, you take a trace down to K, that's a point Q, okay? That's a point Q. It's coming from, from complex multiplication theory. Good, so we have this point Q. What to do with them? Well, you have a map going to E, map it to E, okay? So now we have a map, you have a K rational point, a quadratic point in the elliptic curve. And when D is square free and coprime to N, you can take a quadratic twist, do exactly the same, but use the same field K. One has to be a little bit careful about the condition, the Heegner condition, but that's somehow fine because you have this coprimality with N. Now here's the cross fingers part of the story. Naively, well, this is true. This is true. If you twist an elliptic curve, a quadratic twist, the two torsion is canonically isomorphic as a Galois module. Okay, you can just write down the equation in Weiss transform and see, you will see why. Okay, so you have this canonical isomorphism of Galois modules. So if we are really naive and hopeful, we expect that this isomorphism translates into congruences mod 2 of everything on site. In particular, you will expect some sort of congruence in some way between Heegner points. Okay. Now, of course, that makes no sense because this point is living in E and the other one is living in a quadratic twist. So how you compare those 2 points? What does it mean for them to be congruent mod 2? Well, Daniel Chris and Chao Li figured out what it means. Okay. So you can actually take the p-adic logarithm, the 2-adic logarithm of these points, and then you land in Q2. And Q2 is just Q2. You can compare the one coming from one elliptic curve and the other one, and you have a congruence, okay? There are some conditions that I'm not even bothering to read, but under suitable conditions on the elliptic curve that, are non-trivial. They're somehow restricted, but well, you have this congruence. And what's wonderful about this congruence is that if the left-hand side is congruent to 1 mod 2, in particular non-zero, so is the right-hand side, okay? So if if this logarithm is a 2-adic unit, then the other one is also a 2-adic unit, and the logarithm only kills torsion. So it means that you will get that the Heegner points are non-torsion. Then you can apply Gross-Saguier and get something about the L function. You put it together with Kolyvayin, and then you get BSD, provided that you have some non-vanishing. But then you apply Morty for the non-vanishing. This is the classical story. I'm just mentioning this just to put in context what's going on here. Why it's so important to get non-vanishing of the logarithm. So this is a very impressive theorem by Chris and Chao Li. Quite recent also, 18. Good. So these restrictions are strong. I mean, I wouldn't say they are mild restrictions, but still there are examples. There are examples. And they are really hard to check computationally because, you know, if you want to deal with a Heegner point, you have to somehow do arithmetic over a Hilbert class field. And that's hard because these guys kind of grow. So yeah, so there is a problem there that makes things hard. That restricts the choice of the number field K, the quadratic field K, for the Heegner point construction. Okay. Right, so the Chebotarev set that shows up is a Chebotarev set, but it could be empty. So you actually have to work a little bit there to make sure that it has positive density, okay? And there is also some additional technicalities, according, you know, parity conditions, but well, nothing is for free. Okay, you put everything back together. So we want to prove this theorem that there are this explicit set of primes so that you have this Z is Diophantine in the ring of integers of Q adjoined with the cubic root and the quadratic root. Okay, and for that, as I explained before, we need an elliptic curve over Q so that the rank remains 0 in the cubic root extension and gets positive in the quadratic root extension. So Iwasawa theory gave us a criterion for rank 0. Good, but there is some long list of assumptions. Okay, and then the congruences of Heegner points of Chris and Lee, they gave us a criterion for positive rank. Good, but there is also some bunch of technical assumptions. And these technical assumptions have nothing to do one with the other. So either one separately is really hard to, you know, to be satisfied, and then you put them together. All right, so natural question, is there some elliptic curve that works for both parts of the theory? And well, you can guess the answer because otherwise I would have taken a different topic for this talk, okay? So the answer is yes. So Natalia and I, you know, day and night working on this, eventually found this example. This elliptic curve, the Cremona label is 557B2. This one that you see here satisfies all this, where is it? Here, all these conditions, all of them. And in addition, it satisfies all the conditions in the Chris and Lee theorem. And in addition, it satisfies some additional conditions that make sure that this Chebotarev set is non-empty. Okay, so it does the trick, good. So yeah, well, you have to check all of that, and that's kind of tricky because you need to do arithmetic over Q adjoined with cubic roots of 1. So standard packages in computer algebra systems like Magma or Sage, you know, they can do descent for elliptic curves in number fields at L equals to 2, but it's not implemented at other primes. So you actually need to do a little trick here and there to make it work, okay? And then you have to also prove some little lemmas on precision of integration of p-adic differentials, p-adic integration of differentials, you know. You want a theorem, not a heuristic. You really want to make sure that 0 is 0 here and there. So you need to prove these kind of things, but you know, it works at the end and you get a theorem. Good, thanks for your attention. And during the questions part of the talk, there is a list of papers here if you want to check. The bibliography is really minimal. You need to go to the papers and see what's going on there, but a minimal bibliography in the order that it appeared in the talk. So there it is. Thanks.
Okay. So thank you very much.